So far in this chapter, we've talked about ideal solutions. But for this video, I now want to focus on a specific type of mixture, which involves the mixture of ideal gases, okay, which are going to be inherently different from ideal solutions. And so for an ideal gas mixture, what we're going to consider is the mixing of two ideal gases with that each of these gases have partial pressures Pi, partial pressures Pi at constant constant temperature, constant T. Yeah, I'll just go to the next slide. Okay. All right, and so visually, think of it like this. Say we have one gas that has species 1, moles 1, pressure 1, enthalpy 1, and entropy 1. And we're going to be mixing it with gas 2, which has moles 2, pressure 2, enthalpy 2, entropy 2. And in the end, they're going to form some mixture that has total N, H, S, and pressure, and other thermodynamic properties as well. To characterize this ideal gas mixture, we could talk about the mole fraction, and since we're dealing with a vapor, we're going to use the letter Y. So that's going to be Ni over N. We know that N total, which I call N, is just equal to the summation of all the Ni's. And if you remember from MEP 1 and 2, we know that the partial pressures of a gas mixture are just equal to the total pressure times the mole fraction. Now I mentioned, that ideal gases are inherently different from ideal solutions. And that's because with ideal solutions, right, those are solutions in which the different species have similar interactions and similar molecular sizes. But the ideal gas, the assumptions are much more restrictive, okay? Because with ideal gases, the molecules are going to be non-interacting, right? So there are no interactions. And also, the molecules just have no volume as well, okay? And so these are more restrictive assumptions than, if we were dealing with ideal solutions. But based on these assumptions, that all the molecules in our gas mixture are non-interacting and have zero volume, we could apply a mathematical framework known as Gibbs theorem. Okay? And Gibbs theorem essentially says this: that the partial molar property of a species in an ideal gas mixture at some total pressure and temperature is going to be equal to the molar property of that chemical species in the ideal gas at its original partial pressure and temperature. Okay, so just to clarify some stuff, this Ig means ideal gas. Okay. This P here is the total pressure of the mixture. This thing right here, as you know, is just referring to the pure component molar property value. And this Pi, once again, is partial pressure. So Gibbs theorem says that if you have a chemical species in a mixture, its partial molar property within that mixture is going to be equal to its molar property for the pure component at its initial partial pressure, okay, before you start mixing things together. All right, and so taking this theorem, we could apply that we could apply the concept of additivity to it. So the mixture for the ideal gas, or the mixture of ideal gases, so this is for entire mixture, from the concept of principle of additivity, that's just going to be equal to the summation of the moles of that species times its partial molar property for the ideal gas. We could factor out the total N, so YI MI IG, okay? And then, since we factor out the total N, we could divide regular M by N, so that we get M here, which is just equal to MIG over N. That's equal to the summation of YI MI IG. Right? Because from Gibbs' theorem, this is saying that this at the total pressure is equal to this at the partial pressure. So let me write those in. And this is also at total pressure and temperature. Okay? All right, so that's just kind of the general framework for looking at the molar properties of an ideal gas mixture. But to get a better sense of what these mean or why they're useful, let's look at some specific molar properties for enthalpy and entropy. Okay. All right. So if we take a look at delta H mix of the ideal gas, we know from the definition of our delta mixes is that that's going to be the difference between the actual value of the entire mixture minus the values of the pure. Where we're looking at PI, T here, and for the entire mixture, we're looking at just the total pressure. But we have to remember we're dealing with ideal gases here, and for ideal gases, we know that these things are only a function, enthalpy is only a function of temperature. Okay? All right. And so, we could write these things out. So for HIG, for the total mixture, we know it's a summation of Ni Hi bar Ig. And then for the pure species, essentially we apply the ideal, what we would expect for an ideal solution. Okay. All right. But here, this is not a function of temperature. And we know from Gibbs' theorem up here that these molar properties, partial molar properties, are just going to be equal to the pure molar properties. And so what we would get is just N1 H1 of the ideal gas plus N2 H2 of the ideal gas minus N1 H1 of the ideal gas minus N2 H2 of the ideal gas. And so suffice to say, essentially, the delta H mix for an ideal gas is going to be equal to 0. Okay? So for ideal gases, you don't have any delta H mix. There's no excess enthalpy. Okay? So that's the result we see for an ideal gas. And the reason we see that is because even though from Gibbs' theorem, on the left-hand side we're looking at total pressure, and on the right-hand side we're looking at partial pressure, for ideal gases, the enthalpies aren't a function of pressure anyways. Okay? And so we find that for enthalpies, the total enthalpy of the mixture is just the same as if you just added up the pure component enthalpies. So we looked at enthalpy. Let's now look at entropy. And this one's a little bit trickier. So S mix Ig. All right, and so here we would be looking at the entropy of the entire mixture. And then here we would be looking at the entropy of the pure components. Okay? And so for the entire mixture, if I factor out, well, let me just write it out. For the entire mixture, we get something that looks like this at total pressure P. Right. And we're subtracting off this. S1. Oh, these squigglies should be bars. P plus N2 S1 P. Okay. From Gibbs' theorem, we could write that these are equal to the pure components, but at their original partial pressure. So if we rearrange delta S mix, what we get is that N1 times S1 P1 minus S1 P, okay, plus N2 S2 P2 minus S2 P. Okay? And so I'll highlight here that what we're looking at is the pure component at pressure 1 minus the entropy of the pure component at pressure, total pressure. Same here. And these do not equal 0, right? Because if you remember, when we dealt with the entropy of gases before, entropy is a function of pressure. Right? So because of that, we're going to have a non-zero value here. All right? To figure out what that value is, what we could do, or the approach we're going to take, is we're actually going to use the fundamental entropy equation. So out SI PI minus SI at P will use fundamental S equation. Okay, so let's go do that. And so what we want to figure out is SI at P, SI at PI. So to figure that out, we're going to integrate the fundamental entropy equation so that we get this difference. And on the right hand side, we're going to be integrating this. We're dealing with a system at constant temperature, so that's going to go to 0. Okay? And we're going to be integrating this from total pressure to the original partial pressure of that species. Okay? We know that partial pressures, so if I write this out again, we know that the partial pressures can be written in terms of the mole fraction. These cancel, and what we're left with is just negative R ln yi. Okay, so in each of these parentheses here, we could just rewrite it as negative R ln of yi. So we have n1 negative R ln of y1 plus n2 negative R ln of y2. If I factor out a total n from here, we could turn these into mole fractions as well. And then if I divide by n, what I would have is delta Ig mix molar is equal to the negative R times the summation of yi ln of yi. So this is just the general formula. Okay? All right, so we figured out both the enthalpy and the entropy. So now that we have both of those things, what we could also figure out is the Gibbs energy. Because we know Gibbs, or delta G Gibbs, is just delta H minus T delta S for an ideal gas mixture. Delta H mix is equal to 0, so our delta G is going to be negative T times delta S mix, which we got here. So in the end, our delta G is just this. Okay, and if we expand it out, since here we're just looking at the delta G mixing, if we just want the absolute value of G at some temperature and total pressure, it would be equal to this. Hi of the ideal gas per components at some temperature minus T Si ideal gas at some temperature and total pressure plus RT ln of yi.